Okay, example 3, it gives us f of x equals x cubed plus 6x squared plus 12x minus 4. So it's given us the curve, but it's just used f of x instead of y. And it says find the coordinates of the turning points and determine their nature. So the first step, as always, is the curve ready for differentiation? It is. So the first thing we've got to do is get the general gradient. So general gradient now, because the curve is given as f of x, I'm going to use the notation f dashed x instead of dy by dx. So let's get our general gradient at any point on the curve. So f dashed x is going to be 3x squared plus 12x plus 12, and then when you differentiate a number it disappears, it becomes 0. So we've got the general gradient at any point on the curve. At the turning points the actual gradient is 0. So at the turning point we set the general gradient f dashed x equal to the actual gradient, which is 0, and we solve that to get the x coordinate of the turning point. So we're going to get x coordinate of turning point. Okay, so we set the general gradient f dashed x equal to the actual gradient, which is 0. So we've got 3x squared plus 12x plus 12 equals 0. I'm going to divide through by 3. So we're going to end up with x squared plus 4x plus 4 equals 0. So we're going to solve the quadratic we're left with. We're going to try and factorize the non-zero side. So we're going to use product and sum. So our product is plus 4 and the sum is plus 4. So the only way that's possible is when the two numbers are plus 2 and plus 2. Okay, so break up the middle x term. So we're going to have x squared plus 2x plus 2x plus 4 equals 0. And then split in half, factorize each half. Okay, so product of two brackets equal to 0, so that means both brackets could be 0, and both brackets are identical, so that means that x equals -2. So that means there's only one turning point. So let's get the y coordinate of the turning point. So remember, to do that you sub the x coordinate of the turning point into the curve. So go back to your curve, replace everywhere you see x with -2. So we're going to get f of x. Remember, f of x is just fancy notation for y. So that's going to give us -2 cubed plus 6 times -2 squared plus 12 times -2, and then subtract 4. Okay, so -2 cubed is going to be -8. -2 squared is just 4, and then multiplied by 6, that's plus 24. Plus 12 times -2 is going to be -24, and then we're subtracting 4 at the end. So that's going to leave us with -12. So that's the y coordinate of the turning point. So turning point is -2, -12. Now, Once we've got the turning point, we then have to go ahead and we have to get the nature. And the nature is given by the second derivative, d2y by dx squared. So go back to your first derivative, which was f dashed x, which was up here. So I'm going to differentiate that and get f double dashed x. So f double dashed x. So differentiate f dashed x, we're going to get 6x plus 12. Okay, what we're going to do now is we're going to sub the x coordinate of the turning point into the second derivative to work out what type of turning point it is. So when x equals -2, the second derivative is going to be 6 times -2 plus 12. So 6 times -2 is going to give us -12 plus 12 is equal to 0. Now this is the worst case scenario. The second derivative is 0, so that means that the turning point here could be a maximum or a minimum or a point of inflection. So it's inconclusive, so could be max, min, or point of inflection. So what we're going to have to do to deduce what it is we're going to have to calculate the actual gradient around the turning point where x is 2. So we need to calculate the actual gradient around the turning point. Now here's how we do that. So what we do then is we rule a little table. I'm going to give it a title first. So calculating actual gradient around turning point. So we're going to rule a table with 2 rows, and we're going to have 3 columns. Now, okay, the top row are going to be x values that we're going to investigate either side of the turning point. So the x coordinate of the turning point is -2, so we put that in the middle column at the top. We then choose 2 x values either side of the turning point. So I'm going to choose one to the left in -2 and one to the right in -2. So I'm going to choose -3 and I'm going to choose -1. What we're then going to do is we're going to calculate the actual gradient for each of these values of x. So the actual gradient, remember, is f dashed x or dy by dx. So f dashed x is 3x squared plus 12x plus 12. So what we're going to do is we're going to get the actual gradient when x is -3. We're going to get the actual gradient when x is -2. And we're going to get the actual gradient when x is -1. So let's chuck in -3 in here. So we're going to get -3 all squared. And then we're multiplying that by 3. And then we're adding on 12 times -3. And then we're adding on 12. So that's going to turn out to be +3. We're not worried about the value. All we know is that it's going to turn out to be positive. When we chuck in -2, this is the x coordinate of the turning point. we're expecting the actual gradient to be 0. So just check it. Chuck in minus 2. Minus 2 squared is 4. 4 3s are 12. So we've got 12. And then plus 12 times minus 2 is minus 24. So 12 minus 24 is minus 12. Then add on the 12, we're going to get 0. That makes sense, because that is the turning point. The actual gradient at the turning point is 0. Then we're going to get the actual gradient when x is minus 1, so chuck in minus 1 here. Minus 1 squared is 1, times 3 is 3. 12 times minus 1 is minus 12. So 3 minus 12 is going to give us minus 9. And then minus 9 plus 12 is going to give us plus 3. So the sign of the actual gradient is going to be positive again. So this is what's happening around the turning point. The actual gradient of the tangent immediately before the x-coordinate of the turning point is positive. So if you draw a tangent to the curve, it would be sloping up at that point. At the turning point, if you draw a tangent, it would be a horizontal line, because obviously the gradient of a horizontal line is 0. And then if you drew a tangent to the curve at the point where x is minus 1, the tangent would be sloping upward again, so it would have a positive gradient. So what we notice here is that the sign, SIGN, of the actual gradient either side of the turning point is the same. So what we have here is a point of inflection. So therefore, point of inflection. So our final answer, so the turning point is minus 2 minus 12, and it is a point of inflection. Okay. So it's very important here. Everybody's happy with the setup, but it's when you get the second derivative d2y by dx squared, or f double dashed x, when you get the second derivative and you sub the x coordinate into that, if the second derivative is 0, then at the minute we have no idea what the turning point is. It could be a maximum, a minimum, or a point of inflection. And the only way to determine what it is to calculate the actual gradient around the turning point. So you then need to, as I say, rule a table. The top row is your x values. The middle x value will be the x coordinate of the turning point. Peg an x coordinate immediately to the left of it and an x coordinate immediately to the right of it. And what you're then doing is you're getting the actual sign of the gradient at each point, either on either side of the turning point and at the turning point. So you need to then down here have your gradient, your general gradient expression, and you sub each of the x coordinates into that general gradient expression to get the sign SIGN of the actual gradient either side of the turning point. And by that then you can determine what type of turning point it is. So the tangent is sloping up, then at the turning point it's horizontal, it's 0 gradient, and then it's sloping up again. So the sign of the actual gradient is the same immediately before and immediately after the turning point. So that's why in this case it's a point of inflection. Sometimes when you investigate it, drawing your table, you might discover that it is a maximum, or indeed you might discover that it's a minimum turning point. It won't always necessarily be a point of inflection when the second derivative is 0.